Hi, my name is Kriti Williams, and this is my presentation on the relationship between vapor pressure and temperature, and it's from the chapter Liquid Solids and Intermolecular Forces. So my specific question was, how is vapor pressure related to temperature? What happens to the vapor pressure of a substance when the temperature is increased? And what happens when the temperature is decreased? So vapor pressure and temperature are directly related. And when the temperature changes, the thermal energy will cause the vapor pressure to rise or fall accordingly. So for example, when the temperature increases, the thermal energy is high enough to give more energy to the molecules, and this allows them to vaporize, which will increase the vapor pressure. Similarly, when the temperature decreases, the thermal energy isn't enough to supply as many molecules with energy, so there are fewer that can vaporize, and this lowers the vapor pressure. However, the amount by which vapor pressure increases isn't necessarily the same as the increase in temperature, and this is because a small change in temperature often causes a much larger change in vapor pressure, and that's because it causes a large change in the number of molecules that can vaporize with enough energy. So, for example, if there's a small increase in temperature, there'll be an exponentially larger change in vapor pressure so that it increases. And if there's a small decrease in temperature, there'll be an exponentially larger change in vapor pressure that will cause it to decrease. And this is an example of how vapor pressure and temperature have an exponential relationship. So because of the exponential relationship between vapor pressure and temperature, it can be expressed using this kind of equation, which is like a base form of the Clausius-Clapeyron equation, where here we have the vapor pressure in torr, P vape. Here we have the beta, which is a unitless constant that depends on the compound. And here we have our exponential part of the function, e to the power of negative delta H vape, which is the heat of vaporization in kilojoules per mole, over RT, and R is the gas constant with a value of 8.314 joules per Kelvin mole, and T is the temperature in Kelvin. So this equation can also be written in slope-intercept form, which is y equals mx plus b. So in order to do that, you can first convert it by taking the natural logarithm of both sides of the equation. So you have the natural logarithm of the vapor pressure equal to the natural logarithm of the beta and e to the negative delta H vape over RT. And then here you just simplify further by keeping in mind that the natural logarithm of A and B is the natural logarithm of A plus the natural logarithm of B. So you have here the natural logarithm of the vapor pressure equal to the natural logarithm of beta plus the natural logarithm of e to the negative delta H vape over RT. And then the natural logarithm of e to the x is equal to x. So you have here same thing, natural logarithm of the vapor pressure equal to the natural logarithm of beta plus now it is just the negative heat of vaporization over RT. So that can be arranged into this form here, which is the y equals mx plus b form. And so we have natural logarithm of p vape, which is the equivalent of y. We have negative delta H vape, the heat of vaporization, over R, which is the equivalent of m, our slope. We have that times 1 over T, which is x, plus natural logarithm of beta, which is b. So this equation is used when you have multiple measurements of vapor pressure and temperature. And normally when you have problems that involve this equation, you would normally graph the data points, and you would graph in terms of the natural logarithm of the vapor pressure and 1 over T, instead of graphing just the vapor pressure and the T values as given. And this means that the line created will show a linear relationship between the natural log of the vapor pressure and the inverse of temperature. Then there's also the 2-point form, and it's used when you have just two measurements of vapor pressure and temperature, and you can either use it to find the heat of vaporization, or you can also use it to find values for temperature and pressure as well. So you have the natural logarithm of P2 over P1, the final pressure over the initial pressure, equal to negative delta H vape over R times 1 over T2, the final temperature, minus 1 over T1, the initial temperature. And as I said before, this form of the equation can also be used to predict the vapor pressure of a liquid at any temperature when you know the enthalpy of vaporization, and also if you know the normal boiling point or the vapor pressure at another temperature. So in summary, vapor pressure and temperature have an exponential relationship, So when the temperature increases, vapor pressure increases exponentially, and when temperature decreases, vapor pressure decreases exponentially. And in order to solve equations involving vapor pressure and temperature and heat of vaporization, you can use the Clausius-Clapeyron equation. And this equation has two forms: a slope-intercept form, which is used when you have multiple data points for pressure and temperature. And there is also a two-point form that's used when you have two data points for pressure and temperature. So this was my presentation on the relationship between vapor pressure and temperature and how they are related, what happens when temperature increases, and what happens to vapor pressure when temperature decreases. I hope you enjoyed it, and thank you so much for watching.